So okay, hi, my name is Eric. Welcome to this presentation. I'm a software engineer at Oracle, working for the optimizer team in MySQL. And I will be talking about hash join in MySQL, which is a new feature in MySQL 8.0.18. So the agenda for today is that I will first talk about how we got to the point where we were able to implement hash join. We have done some major refactorings, which are now finally starting to pay off. I will go through what hash join actually is, before going into details about hash join in MySQL 8. What it is, what kind of performance you can get from it, how you use it, and other things that can be useful to know about hash join. So first, some background history. For the longest time, MySQL only supported variations of the nested loop algorithm for executing joins, which is, of course, the basic nested loop with index lookup. And we also have the block nested loop, which is a nested loop with an in-memory buffer for some speed up. And because we only supported nested loop, our executor and optimizer for that sake has been very focused around this nested loop execution, making it very hard to extend with other join algorithms that may not be a nested loop kind of algorithm. And for the last 2 years, we have been working very hard on implementing a brand new executor, an iterator executor, which is now released in 8.0.18. So this new executor is based on the Volcano iterator model, which is sort of like the textbook example on how to implement an executor. And one of the basic ideas in this model is that all operations should share a common interface. In MySQL, this interface has two methods, which are init and read. Init initializes the iterator for reading, making it ready for returning rows, and read simply returns the next row from that iterator. Another important thing is that each operation is contained within one single iterator, so that responsibility and things are not scattered around the code base in different places. So things are more self-contained now. And because of these two things, we now have a much more modular executor, which allows us to implement new features faster and making things a lot easier to understand. A colleague of mine usually compares the old executor to a jigsaw puzzle, where pieces can fit in only one specific way, while the new executor is more like Lego bricks, where you can connect them like you want. So by having this new executor, hash join was just a new iterator. Of course, there are some details around it. And there are other features now as well, which stems from this new executor. Explain analyze is one of them. We have a new tree-based explain output, which is also very nice, and thanks to this new executor. So an execution tree can be visualized something like this, where you have two table scans on the bottom. The left side has a filter after it. Both of these go into a hash join iterator before ending up in a sort. And because all of these share the same interface, you can easily imagine replacing the hash join with a nested loop, for instance, or any other operation. So what is hash join? Hash join is a join algorithm that uses hashing to find matching rows between two inputs. It was first described in the mid-80s, so this is a fairly old executor join algorithm. In order for hash join to work efficiently, it requires at least one equijoin condition. An equijoin condition is a condition on the form column equals column. You can, of course, have multiple equijoin join conditions in the same query. And hash join usually comes in three different flavors. You have the classic hash join, you have the Grace hash join, and you have the hybrid hash join. Each of these builds on top of each other, adding a bit more complexity. You also have more exotic variants like a distributed hash join, but these are kind of the three basic hash join flavors. So I will go through each of them to explain how they work, in order for you to understand how hash join works in MySQL. So for these examples, we are going to join together two tables, which are countries and persons. We will join them on the column country ID, which simply describes which country a person lives in. The classic hash join is divided into two separate phases. They are called the build phase and the probe phase. So in the build phase, one of the tables are designated as the build inputs. Of course, it doesn't have to be a table. It can be any other input, of course. The build input is loaded into an in-memory hash table, where the hash table key is the part of the join condition that belongs to the build input. In this case, that's the column countries.countryid. Once all the rows have been loaded to the hash table, the build phase is complete. The next phase is called the probe phase, and the other table is called the probe table. For each row in the probe table, you create a hash table lookup key using the part from the join condition that belongs to the probe table. And for each match you can find in the hash table, you return a joined row to the client or to the output or the next step in your execution tree. Once all the tables from the probe input has been read, the join is complete. So the benefit here is that you read each input only once. But in order for that to work, the build table has to fit in memory, of course. That is why we choose the smallest table as the build table, measured in size or bytes, not in number of rows. Larger inputs can also be handled like block nested loop does, where once the hash table goes full, you do the probe phase by reading the entire probe input. You then clear the hash table, continue reading the build input, filling it up with the rows. You then scan the entire probe input again and continue doing this until you have consumed the entire build input. And the drawback here is that you end up reading the probe table multiple times, which is something we do not want to do. We can be more efficient than that. So in order to handle larger inputs, the Grace hash join was introduced. It was first implemented in the Grace database system, hence the name Grace hash join. The first step in a Grace hash join is to partition each input out to a set of smaller chunk files on disk. You have equal amount of chunk files for both inputs, and which file to put a row in is decided by doing a hash over the part of the join condition that belongs to that input. And the result is that we can guarantee that matching rows are located in the same pair of chunk files. So after the partitioning phase is done, you can do the classic hash join algorithm over each pair of chunk file. You take the first chunk file from the build input and load it into the hash table. You then can do the probe phase using the chunk file from the probe input. You clear the hash table, load the rows from the next chunk file, and you continue to do this until you have processed all the chunk files. So this is sort of like a divide and conquer algorithm, where you take a big problem and you divide it into a set of smaller problems and handle them. Each input is still read only once, but you have to write it out to chunk files and read these chunk files back again. There are two things to note here. One thing is that you compute each input only once. And by that, you can think that each input to hash join can be a more complex subtree. It can be another join or anything. So by writing these out to chunk files, you can compute the subtree only once. And when you read the files back, it's pre-computed, right? Compared to a classic hash join, where you end up computing the probe input multiple times for each time you read it. The other thing to note is that reading from a chunk file is a lot cheaper than reading from a table. You do not have the overhead of locking, you don't have to care about transactions, multiverse and concurrency control, etc. So the cost of reading from a chunk file compared to a table is very low. The drawback of the Grace hash join is that for small inputs, you end up doing unnecessary disk I/O because you could have done everything in memory, right? That is where the hybrid hash join comes in. It's a combination of both the classic and the Grace hash join. You start out by trying to do everything in memory. You read as much as you can into the in-memory hash table, and if you are able to fit all rows in the hash table, you can do the classic hash join, right? If at any point the hash table goes full, you take the rest of the rows from the build input and write it out to chunk files on disk as in the Grace hash join. During the probe phase, you do the normal probing in the hash table, send out all matching rows to the output. But in addition, if you did spill to disk during the build phase, you also have to write all the rows out to chunk files. That is because one of the rows may match one of the rows that you did write out to chunk file from the build input. So once you have read the probe input once, you can now do the classic hash join for each pair of chunk files, which is what we did for the Grace hash join. So once that is done, you have completed the join. So this gives you sort of the best of both worlds. You get in memory, if possible, if you have small inputs, but you also get the benefit of spill to disk for large inputs. And you also still are computing each input only once. So this brings us to hash join in MySQL 8. Hybrid hash join is the algorithm we implemented. And since hashing is used so much for hash join, we chose to use the hash function xxhash, which is a familiar, good quality, fast hash function. If we decide to spill to disk, we will write up to 128 chunk files per input out to disk, which means each hash join iterator will potentially write up to 256 files on disk. And this upper limit exists because so you don't risk hitting the open files limit that MySQL has. With hash join, you have no guaranteed output ordering anymore, which you might have been used to with the nested loop algorithm. 8.0.18 supports inner hash join, but in the upcoming 8.0.20 release, we also added support for the rest of the join types: semi-join, anti-join, and outer hash join. Currently, hash join replaces block nested loop whenever possible, which is in almost every possible case. Since hash join replaces block nested loop, you have to use the optimizer switch block nested loop to enable or disable hash join. It is enabled by default, and if you want to see whether or not your query is using hash join, we recommend you to use the new explain format equals 3 output. That's the one explain that gives you an accurate representation of our iterate execution tree. Here you can see an output from explain. Very clear, you can see that we have an inner hash join. You can see the join condition. You can also see which of the tables that were chosen as the build input. In this case, it's the countries table. And here we turn off the optimizer switch block nested loop. And you can see that the query is executed using nested loop instead of hash join. If indexes are available, the optimizer will tend to favor nested loop with index lookups instead of hash join. If you want to force a hash join to be used, you can either use the ignore index syntax or use the new invisible index feature to turn off indexes and force the optimizer to choose a hash join plan.
Is there not a query hit to do that?
Oh, you can use the optimizer hints as well. Yeah, you can. And the system variable join buffer size controls how much memory is available for the hash table. But please note that a larger buffer size does not necessarily mean better performance. Having larger hash tables has this cost by doing rehashing and general maintenance. So in some cases, doing things on disk may be faster than doing everything in memory. So this is where you need to benchmark your queries to see what fits for you. So I have 5 minutes left, I think.
Yeah.
Okay, so I will give you some simple performance numbers. Here we have 2 single column tables. Each table has around 42,000 rows, integer values, uniform distributed. And this is all MySQL 8.0.18 with default settings. If I execute this simple join with block nested loop, we are comparing to block nested loop since we are replacing it. The join can be executed in almost 50 seconds. With hash join, however, we can do the same join in 0.03 seconds, which is an improvement of around 1,600 times. The main reason for this speedup is that doing a hash table lookup is a constant time operation versus the linear search a block nested loop has to do. And so this gives you very good speedups for these kind of queries. If you add more rows, let's add 32 times more rows, we can still execute a join in 1.3 seconds using hash join, which is still far less than block nested loop. We can add up to, let's say, 5 million rows. We can still do the join in 10.6 seconds, which is still faster than block nested loop with 42,000 rows. Here we also get the benefit of spill to disk since the inputs are so large, and we have a low join buffer size, which is the default setting. In the first example, tables were small enough to fit in memory. And hash join can even be more efficient than a nested loop index lookup. In this case, I've added an index on both columns. So the query plan is now a nested loop with index lookup. And execution time for this join is 12.17 seconds, which is 1.5 seconds slower than hash join. And the main reason for hash join being faster here is that probing a hash table in memory is faster than doing a secondary index lookup. If you had fewer duplicate values, nested loop would probably be quicker than hash join. That was all I had. So if any questions? Yes, Simon?
One question, the join buffer size, that's something that's per thread, depending on whether you're running thread.
Yes, that's per thread and per hash join iterator.
So clearly,
Okay.
is there any control on memory usage there? Because it might be that you might prefer to limit the number of concurrent hash joins that are running to preserve memory and not suddenly jump and hit a memory issue.
Okay, so the question was the join buffer size is per thread, and do we have a global control of it?
Yeah.
Yeah. Yes, it's per thread, and no, we don't have global control of it currently. So the memory usage is, or the join buffer size is per hash join iterator.
Yeah.
So one query may use multiple times of that buffer size.
Queries going on, clearly you could do thread pools and things, that depends on which implementation you're using and things, but if you're not doing that, then potentially...
It's exactly the same as now.
Yeah, but the point is that you're suddenly changing your behavior and all of a sudden you've got 30,000 queries running on a thing, you suddenly change to use this, you take your OO in your box.
But that's the same with block nested loop as today. Block nested loop uses the same buffer size.
Let's do the same thing.
Okay. So there's no change, behavior change here. No, not nested loop, but block nested loop.
In some cases, you don't need, if you have lots of tables, you don't need for those to does an index. If you add this for everything, then you get a huge thing. And you also have a problem that you can have 10 queries running, and all of those use is 256 open files, which basically tries to serve.
Yeah. So his comment was that with many hash joins doing large joins, you can get a lot of files on disk, which can, of course, create some contention on the disk and problems.
Why don't you use many files instead of just having a pending on a file, which would basically would be the same thing?
Why we use many files instead of one big file?
One file and just have it logically in your block.
That we use many files because of simplicity.
Storing a pointer doesn't sound that common.
More questions?
Thank you.
You showed that actually, when you have the two tables with the same size, adding an index can actually give you a worse performance, right?
Yeah, in some cases, yes.
Which is probably when the two tables had exactly the same number of rows, right?
Mm.
So, are there guidelines, or is there anything on the roadmap that will kind of choose the best strategy, even when the index is available?
So you're asking if we are going to change the optimizer. Of course, we are thinking about that to, of course, choose a better plan for these cases, yes. Currently, we haven't changed anything, but we are thinking about it.
Okay, thank you.
So what we store in the hash table? Oh, in the files on disk? We store exactly the same as we store in the hash table. We store whatever from the row that is needed to complete the join. If you do a select star, we must store the entire row. If you select one column, we store that single column. Yeah, so the chunk file is not the entire table necessarily. And also note that this can happen, of course, after filtering, so that you don't have to put the entire table down to chunk files. Yes. Yes. So where do these chunk files go? The same places all temporary files in MySQL go.
Thank you, Rick.
Okay, thank you.